All right, we're live. Hey, Pham. Nope, I mean Physics Fam. This is Mr. Kennedy, along with
Me.
What's your name?
Finn.
And he did not comb his hair, but he promises to comb his hair next video. We are going to take a look at problem number 1995. M1. Pretty straightforward problem. Deals with a collision, an elastic collision, some momentum, some energy. Should be something that you might see on the actual exam, and not too tough. All right, so we have this table. We have a block that's going to be moving, and we have a stationary sphere. Luckily, my assistant, the one and only, what the heck is that? Turn off that. Is that cell phones? My one and only assistant is going to demonstrate what is actually happening here. Fortunately, he doesn't have a cube. He has a larbar, and he has a dryer ball. All right, assistant, have at it. There we go. Do it one more time. That was pretty good. All right, so we have the cube moving with some velocity, hitting a stationary ball. And then we're going to talk about momentum and energy there. Whoa, awesome. Okay. So, it gives you a graph, and it asks you for impulse. If I can have... Are you eating my demo?
I was hungry.
Oh, God, you just can't get good help these days. You can't. Get my super fancy, sophisticated stand. All right, they ask for impulse. And as we remember with impulse, it's like the good old egg toss. You can calculate impulse. Ooh, that was from Wonder Woman's problem. By multiplying the force times the time. Increase the force, you can decrease the time, or increase the time, decrease the force. That's the old swing method of the egg toss. Can you hang that up at the assistant? Actually do something useful. Put the larbar down and hang this up. Oh my gosh. Anyone want some kids? I'll give you a good price. And maybe a dog. Wife. Don't come on and say. Today, we don't get all day. All right, let's call that good enough. Ooh, closer. Impulse is just change in momentum. We can also say that that's just force times time. Well, that is the case when it's a constant force over some time interval. But is this a constant force over some time interval? No, we don't have a horizontal line of a constant force. We don't even have a triangle to make it easy. We have a trapezoid. But still the same idea holds true. If we want to take the integral, the integral is just we're summing up all those forces times a little bit of time, or we can say area on the curve, same thing. So if we just look at that area under the curve, we got the purple bit, red bit, green bit. They got what? 1/2 times base times height, 1/2 times 4 seconds times 2 newtons. That triangle is actually going to be the same size as that one. And then we get that little square in between, 2 times 2. And we get an overall impulse of 12 newton seconds. That's the old unit of impulse. Now, I jumped the gun in my solution a little bit here. They're asking for in I, what are they asking for? They want to know the speed of the cube immediately after the collision. Can you show us the cube again? No, because he ate it. Oh my God. All right, well, the cube was the one that was moving pretty fast. It was going 26 meters per second, pretty light. And the ball wasn't moving at all. And we know this is a law of conservation momentum right here. So we know its speed and its mass. We know the mass of the ball and its velocity before. We don't know the velocity final of the cube. And we don't quite know the velocity of the sphere yet. So this is actually solving for C, but I have to do B first. I have to use down there. B says that the change in momentum is going to be equal to your impulse. Whoa, 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 whoa. We just figured out impulse was 12. So we can chuck that in there. And then change just final minus initial. Whoa, initial momentum. Who's there? Want to come in? Hey! Look! A new star here. Say hello. Introduce yourself. This is AP Physics. This will be what you'll be taking. Jolie's going to be taking this exact same class in 3 years' time. Right, Jolie?
No.
Now, where were we before we got interrupted? Initial momentum is 0 because it's not moving. And the mass of that object is 5 kilograms, so we can solve for final velocity. Just divide both sides by, you eat a little bit less loud.
Yeah, really.
Final velocity is 2.4. We chuck that 2.4 in there, so that's how fast that, what was it? That's how fast the ball, the sphere, is moving. So from that, now we got all but one variable, and we can figure out how fast the cube is moving. Good old 2 meters per second. Any questions? All right. Finn, load up the next page. Try not to screw this up. What do you need help with? That's what we're just doing. You should have paid attention.
Wait, how do you find it though?
In a collision?
Yeah.
That's crazy. My daughter, who's a freshman taking models of physics, is asking sort of the same question.
Look at it.
You set up an equation. Law of conservation of momentum.
So
Momentum before equals momentum final.
But there's momentum. I don't have momentum.
Can you see me and Finn are doing something?
Okay,
We're becoming famous. Remember to like and thumb up and subscribe, and we're making a lot of money from these videos, so we need you to comment down below. What the heck does it ask for? Oof, we're already in 8 minutes. Let's do this fast. We did the speed of the cube. It's traveling to the right because it's positive. I didn't mention that, but you guys should know that. D asks for determine the kinetic energy dissipated in the collision. So momentum is always conserved. Kinetic energy is conserved, but if we're talking about a system and collisions, there's a lot of deformation, there's sound, there's heat, all that escapes out of our system that we can't really track. So we are going to lose some kinetic energy here. Initial kinetic energy was 169 joules. And then we add up the two kinetic energies because we have the masses and we have the velocities. They get a lot slower. This one goes from, 26 meters per second to 2. This one went from 0 to 2.4, so it actually gained velocity, but we lost a whole lot of velocity, and that's the really key here. That sucker gets squared. So we go from 169 to 15.4. That's a whole big loss of 154 units of energy, which is not the Nominex, not the Aldi's, not the Trader Joe's, but the Joule. We have another girl sneaking up on us. Oh, jeez. This is the smartest one, Charlotte. And then Finn, yeah. He does all right. All right, we got to finish this up. Charlotte, anything to say? Okay. All right. We got that energy time for both to hit the ground. I don't know if it asks that. It's just when they do hit the ground, how far are they going to be apart? If we ignore air resistance, yes, they're both dropping from the same height. So we get that old 2 times delta y divided by g or a. They're both going to be in the air for 0.5 seconds. You know, a fired bullet and a drop bullet hit the ground at the same time. You just take 2 times the distance it drops, divide by 9.8 or 10, take the square root, you got yourself your time to hit the ground. Then one's moving at 2, one's moving at 2.4 horizontally. So we just multiply that by 0.5. One's going to move a meter, one's going to move 1.2 meters. They're 20 centimeters apart, and Bob's your uncle. Hooah. Okay, anything else to say? Finn? Where'd Finn go? All right, Finn, don't eat the dryer ball. Charlotte, anything to say? Okay, peace out.
And subscribe.
There you go. How can you not like and subscribe that one?